temperature data incorporates mean precipitation data, predicts the type of terrestrial biome expected for a specific set of climatic conditions, for all of those. I was really lazy on these. Which one of these terrestrial ecosystems would probably have the shortest growing season? A grassland, a coniferous forest, a tropical rainforest, or a temperate deciduous forest? So which one would have the shortest growing season? You can probably narrow it down to two pretty easily, right? Can you narrow it down to two?
Why does it use Please don't answer that question.
So I don't know if it'll benefit any of you, but within about 2 weeks, they're going to change every single computer in building 25 and 26. They're supposed to be putting in the most spectacular, brand new supercomputers in every single classroom. Now that we're all done fighting with this.
Exactly.
So if you're taking classes here in the fall or even in the summer, you might be able to enjoy that.
We could see the teachers tackling with new technology.
Yeah, well, yeah, hopefully that's not going to be too much of an issue, but hopefully it'll just work. Okay, Eric, are we there? One more? Not there. It's huge. Isn't it you?
This thing doesn't work anymore.
Oh, okay.
It's full of lost.
But what, so you haven't been reading in at all tonight? No. Okay, I just didn't notice. Okay, there we go. Yeah. Grassland is probably not a particularly bad guess, but most of the grasslands actually would have summer that would be a little bit longer, almost like what you would find in the temperate deciduous forest. So really a coniferous forest would probably have the shortest growing season. I'm not sure that's the best question. Okay, so here's the good news. Ready for the good news? I've only got 3 more sets of PowerPoints to go through. Bad news is one of the 3 is supposed to be done in the next half hour. That's not going to happen. Because I've only got 3 lectures and one of them is tonight, right? So we're a little bit behind. So I'm going to go a little faster. I'm going to try to pick up just a little faster. So you might remember at the beginning we talked about these different levels of ecology. Just because ecology is such a broad field that we want to be able to sort of focus in on particular aspects of it. So organismal level ecology, you'd be focused on different aspects of this animal's biology that make it suited for its environment, how it captures prey and how it escapes predators, stuff like that. Population level ecology is where you're going to be focused not on, why does the mouse have big ears, but instead you're going to be focused on aspects of the demography and changes in the actual size of a population. This is what we're going to focus on now. I mentioned last time, I think, you could take a semester-long course on population ecology, and there's an entire chapter in, I think, both Brooker and Campbell, definitely Campbell has a whole chapter on it. You're going to get the kindergarten quickie version here so that we can get through it. But this is what we're really going to go on in earnest in just a moment. Community level ecology, which we're going to kind of focus on in the lab, has to do with the interaction of at least 2 different species. Typically, you're looking at aspects of how their populations affect one another, so there's a population ecology aspect to it, but you're always focused on interactions, whereas a population level ecologist is really more interested in a single population. Ecosystem level ecology incorporates abiotic factors. Landscape level ecology looks at different ecosystems and how they interface with one another, and then you could have global level ecology that would look at larger sort of global patterns. But this is what we're going to focus on now, right? So population ecology really focuses on how biotic and abiotic factors influence the density, the distribution, the size, and the age structure of a population. And of course, this is a particularly interesting level for an evolutionary biologist because populations are the fundamental units of evolution. Evolution happens in a population. It doesn't happen in individuals, right? So you could imagine this is a population, and what we're going to want to be able to model here in just a little bit is how populations change over time. So if you go and look at a population of these little birds, for example, there might be 100 individuals, you know, one year, and then the next year you go back and now there's 200, and then next year you go back and there's 50, right? So you're going to want to see how that population size changes over time. And you'll see when we model this, we need to figure out what are the ways in which a population can gain individuals or grow, and what are the ways that a population can lose individuals. So obviously, individuals that are born into a population would increase the population, and individuals that die, like this poor little thing here that's completely unsuspecting stuff being devoured by this, would decrease the population. You could also have immigration, which brings individuals in to join from another population, and you could have emigration, which would be individuals leaving. You'll see in a few minutes when I set up the model for population growth, we're actually going to ignore these two. And the only way that we're going to gain individuals is by births, and the only way we're going to lose them is by death. The only reason we're going to do that is because otherwise the math is going to get bad. And I'll show you how you could simply just add other terms to your equation, but you're not going to want to. You're going to be happy that we're going to only use these two, because otherwise the equation gets longer and more complicated. And I want you to have an equation you can work with. Okay, so we can talk about density. Density, we're going to want to know how big a population is, but we also want to know sort of how many individuals there are per unit area, right? So if I just told you, you know, there's 100 kangaroo, well, I mean, if that's in an area that's as big as this classroom, they're all on top of one another, right? But if that's 100 kangaroos in like, you know, 300 square miles or something, then they're pretty spread out. So that's what density refers to. It refers to how many individuals you have per unit area. And this can be dynamic, it can be changing, just like the actual size of a population is always changing. And that brings up an interesting question of how do you know how big a population is? So this picture's out of Campbell. It's these little sheep in Scotland, and these are supposedly the closest relatives of domesticated sheep. They had a little population on one island, they trapped some little individuals and let them go on another island where they had no predators and tons of food, and they were able to monitor the population. They've been monitoring this like since the 30s or something. And part of what they wanted to see was, would the population size change, you know, or would it sort of just increase, or would it increase and decrease? And as it is, it actually does go up and down. And so then they can come in and sort of look at what the factors are that might do it. But how would you estimate like the number of sheep or the number of gazelles in Africa? How are you going to even do that? How do they go out and tell you how many of an animal there are? Do you know? How would they do something like that?
Tag it?
Okay, well, so you could go out, like, let's imagine you set some traps or something, and you trap a bunch of gazelles somehow, right? And then you would tag them, and then you let them go. So I trapped 100 gazelle, and I tagged them somehow, and I let them go. How's that going to help me figure out? I'm basically doing a marker recapture technique, right? So how's that going to help me figure out how many of them there are out there? I could go out again and capture another 100, and then I could see of those 100 that I captured the second time, how many of them have the tag on, right? Let's imagine I had one scenario where I had 50 that had the tag of the 100, and another where only 10 of the 100 had the tag. So which would give you a larger estimate of the overall population size? The one where you captured 100 and had only 10, right? Are you following that? Right? If I catch 100 and I tag them all right, and I let them go, then I catch another 100, and of those 100 I caught, 50 of them have a tag. Well, that means there's not a whole lot of them out there, right? But if of those 100 I catch the second time, only 10 have the tag, or maybe only one has the tag, the fewer that I catch that I had marked, the more it indicates are probably out there that I'm catching, right? And you'd imagine doing that with like some kind of a marine mammal or something too, right? How do you estimate the number of dolphins that are in the Gulf, for example, or something? That'd be a really hard thing to do, right? It's probably largely going to be done through marker recapture that way. Maybe with terrestrial animals, you could imagine things that herd and stuff. You might do aerial photographs or something like that. You might be able to get sort of general counts of taking large aerial photographs or something. But it's not trivial. It's funny how, you know, we talk about, you know, what the densities and population size of animals are, but you never really think about all the work that must go into trying to actually get some kind of an accurate estimate of that. Okay, so we can also think about dispersion patterns. So this has to do not just with density, but whether or not organisms are arranged in a particular way. It basically refers to variations in local density. So you can imagine sort of three general patterns, one where organisms would be clumped, one where they would be uniformly distributed, and one where they would be random. And you could have the same density in each one of these, you just have different dispersion patterns, right? So this one would be an example of clumped, right? Because like the starfish are all kind of together in one spot. The penguins would be sort of uniform, right? They each need their little territory where they're gonna have their little eggs, so they space themselves out so that nobody's too close to their neighbors, right? And then like the dandelions in the field here, you sort of picture as being random, right? It's not nice and evenly distributed. There's some clumps, but then there's some where they're separated too, so it's not really following a real pattern of dispersion. And then we come to this big topic of demography, which basically refers to population statistics, so birth and death rates, and how those would change over time during an individual's life. And we can present these two different ways, in a life table or a survivorship curve. So I'll show it to you first in a life table. This is a life table for a Belding's ground squirrel. And they've divided the life table into two parts, one for males and one for females. There's some little glitches in this. If you read this, the numbers don't quite add up because they say things like it includes 122 females and 126 males that were first captured as 1-year-olds and therefore not included in the count of squirrels aged 0 to 1. And so there's some little caveats down here, but I'm just going to walk you through. In general, you'll notice that you have these different age classes, right? Of 0 to 1 years, 1 to 2, 2 to 3, 3 to 4. So basically you go in and you say, this is how many females there were that were alive at the beginning. This is how many males there were that were alive at the beginning, right? The proportion that are alive, well, they're all alive, right, at the beginning. And this is how many croaked, right? Right? And so then you can estimate what the death rate is. And then from all of this, they're able to estimate this average additional life expectancy, or average additional remaining life expectancy, right? And so you can tell that what happens here is as you go down, obviously we're getting fewer and fewer and fewer squirrels, right? You have one little ancient squirrel down there that lived for 10 years somehow. The males didn't fare that well, right? The oldest the male got was like about 5, right? But you'll notice if you look at this average additional life expectancy as they're estimating it, these numbers are not changing a whole lot. So what that really means is, you know, if you're a squirrel that's 2 to 3 years old, you only are expected to have about another 1.5 years of life. But notice if you're a squirrel that's 7 to 8, you're expected to have about another 1.5 years of life. And if you're a squirrel that's like 1, you're only expected to have about another 1.5 years of life. So what that basically means is that the death rate is kind of constant regardless of what age you are. Yeah? In a squirrel. So you can graph this. This is called a life table. This is called a survivorship curve, right? And what it basically looks at is the number of survivors, or you could think of the y-axis as being the average expected remaining lifespan, right? And then here's the different age classes down here. So you notice the line's a little steeper for males, but basically they have the same curve where you're sort of almost as likely to die when you're young as you are when you're old, right? It's basically a straight line. You can do this for a whole bunch of different species, and you'll see that you end up getting sort of 3 general patterns. A squirrel has what we call a type 2 survivorship curve. It's basically a straight line. You're just as likely to die when you're young as you are when you're old. Humans would have something closer to what's called a type 1 survivorship curve. How would you interpret that? Here's the lifespan, right, of humans. You can think of this as age classes if you want. And here's number of survivors, or basically the expected remaining life. So how would you say that then?
The older you get, the less you have, or the more likely you are.
You are to die. That's right. So we have really good parental care. We take really good care of the young, right? We tend to have very few children in a family, and they're well cared for. So you're very unlikely to die when you're young, right? There's obviously infant mortality stuff. This is a very kind of simplified curve, right? But as a human, you're much less likely to die when you're young. You're much more likely to die as you reach old age. Yeah? How about an oyster, though? Oysters have 100 gazillion kids. They don't take care of any of them, and most of them end up being fish food. So if you're a baby oyster, you have like a 1 in 100,000 chance of making it. But if you do make it, you live for a really long time once you get established in 7, right? So you're much more likely to die as a juvenile than you are as an adult, right? This would be a type 3 survivorship curve. And there's a lot of organisms that actually have some kind of a mixture of these 3 curves. Okay, you're all thinking to the final and what kind of crazy extra credit questions I could ask. Copy, paste. What's the name of this graph? Survivorship curve. And then if I asked you to explain the difference between a type 1 and type 2 and a type 3 or something like that, you could do it, right? This is a survivorship curve, and notice basically a graphic representation of a life table is what it is. Yeah. So now we're going to switch gears for a second. We've looked at the idea of a life table and survivorship curves. Now we're going to look at what's called a reproductive table. So this isn't going to be focused on like how many average remaining years of life you have and stuff. Instead, we're going to be looking at how fast can you crank out babies, right? So but it's going to be set up by age class again. So it's an age-specific summary of reproductive rates in a population. And you will notice the reproductive table that I'm going to show you in a second has only female squirrels on it. This is because if you're an ecologist, right, and you're trying to study this, it's much easier to just keep track of females than it is males. And the reality is that for most animals at least, because all of the energy, all of the resources are given by the female, females really determine what the reproductive rate is. If you want to know how fast can squirrels make baby squirrels, you really don't need to think about the males at all. You can almost just assume that there is just an infinite amount of squirrel sperm babying the entire system. Because one little male squirrel could run around and impregnate a zillion different females, right? And he doesn't have anything to do, right? They're the ones who have to actually carry the babies, suckle the babies, and wean the babies, and raise the babies, right? So what I need to know is a female squirrel, how fast can she crank out babies? She's not going to be limited by sperm. Sperm is never limited. Males are basically not really worth anything, right? They really aren't in the grand scheme of things. If you can figure out how fast the females in the population can crank out babies, that's the limiting factor. It's not going to be the males. The males are never going to be limiting unless you have a system where the males are really important for raising offspring or something like that, but that's not the case in most animals. Okay, so you'll notice that we're going to be interested in a lot of different things regarding a female's reproductive biology. So what is the age at which she first reproduces? How young is she when she first has her babies? How often does she have babies, and how many babies does she have? So if you look at these female squirrels, and you'll notice we've got only females now, obviously when they're really little, none of them are having babies, right? So when they're babies, they're not having babies yet. But by the time they're 1 to 2 years old, 2/3 of them are already having babies, right? And you can see what's the average size of their litter. So they're having 3.3 babies on average. What's kind of remarkable is notice by the time they're 2 to 3 years old, 90% are having babies. By the time they're 5 to 6, they're all having babies. And what's really remarkable is Grandma Moses down here still having babies, right? This poor little ancient squirrel that made it through at 10 years old, she's still cranking out babies. And what's more, she's not all that much behind these guys, right? She's still having 3 babies a year. That's crazy, right? So you'll notice the litter size sort of peaks when they're about 4 or 5 years old, but they're reproductive all throughout their life. They're constantly reproducing, right? We say that a species that does this is Iteroparus. Itero means like to repeat. They have repeated reproduction. Like an iteration is something that you repeat when you say it, right? Repeated reproduction throughout their life. We're Iteroparus, right? A person can have offspring throughout their life, right? You can sort of have variations on iteroparity. So, for example, birds don't have babies in the fall. Right? Most birds have their babies in the spring, so they have a seasonal iteroparity, but every spring a pair of birds could have babies, right? The chimpanzee is iteroparous as well, but it wouldn't be sort of very clock-like, right? Instead, you'd have sort of this continuous iteroparity, or it sort of almost appears to be random in when they have them. Other organisms are what we say simulparous, so iteroparous versus simulparous. Simulparous is sometimes called Big Bang reproduction. This is when you live your whole life, and then right before you're ready to die, you have all your kids, and then you croak, right? So you don't have to deal with them. You remember squid are like that. You remember the squid all dying in the movie because they were laying their egg cases. As soon as they lay their egg cases, they die. Salmon that go upstream and spawn and then die. There used to be a question in the moat lab that asked, why does moat have to keep replacing their octopus? That's because every time it lays an egg case, it dies, right? That's the end. This shows you a century plant here. It makes this big, spectacular flowering stalk, and then it dies. This is a picture I took on the slopes of Haleakala in Maui, right? This is a Hawaiian silver sword. It's the same thing. It lives its whole life as a little plant like this, and then it sends up this spectacular flowering stalk, and that's the last thing it does, and then it dies. Yeah. Okay, so obviously reproduction is important. It's a major driving force, or you could argue the major driving force in all biology, right, is reproduction. Because really your goal as an organism is to make sure that your genes are represented in the next generation. That's why people have kids. That's why people are driven to have kids, right? And why reproduction is such a strong driving force. But there's trade-offs here, right? If you like have a couple kids and then you die in the process of doing that, that potentially prohibits you from getting more kids, right? You want to get as much of your genetic material into the next generation as you possibly can. So there's typically some kind of a trade-off where you want to support your kids, but you don't want to do it to the extent where it actually like kills you and prevents you from getting even more of your genes into the next generation. So all of this time and energy and nutrients that go into kids, and you'll notice there's lots of different strategies. For as many different species as there are, there's lots of different strategies. Some species have zillions of kids and don't do anything for them with the expectation that a couple will make it somehow. And others put a lot of resources into a very small number of kids with the expectation that they all will make it because there's so few of them, right? And you could say which one's better. Obviously, they both work, because I could give you a list of hundreds of examples of both types of strategies and all different types of intermediate strategies. This kind of is a little illustration of the types of trade-offs you see. So this is a kestrel. This is out of Campbell again. And here they have like normal little kestrel nests. And for some of them, they pulled a couple eggs out, and those are these guys, and then they took those eggs and they put them in somebody else's nest over here. So you have some kestrels with just the right number of eggs, and some with too few, and some with too many. And you'll notice that when you have fewer kids, you do better. And in this case, the males actually do better because they care for the young. And if you have too many kids, it decreases your ability to survive to the following winter. Yeah? Having kids is a cost, right? And several people in my other class were like, oh, yeah, yeah. Because if you have kids, you probably realize it, right? They're a little bit of a drain on you. So it's got to be some kind of a balance. It's got to be, you want to make sure that you are having kids and investing in that next generation. But you need to balance that with your own interests so that you're able to have more kids or somehow more get your genetics into the next generation. So this kind of shows you these two types of strategies. You'll see that a species that basically is designed to just crank out kids by the bazillions, but with very little interest in any of them, is called an R-selected species. So something like a dandelion, hopefully you know this is a fruit. You all know that, right? With a little parachute on it, right? This is an achene. It's kind of like that little fruit that's on the outside of a strawberry. There's one little seed inside, and they make zillions of them. They blow them out with the wind. Very small. Not a lot of resources put into any one of them, but the expectation is that a couple will take, and that's good enough. A K-selected species would be something a little bit more like that. So fewer kids. So an oak tree would make fewer seeds, fewer acorns, but they're larger, they're more nutrient rich. The expectation is a larger number of them is going to survive. So again, it's very hard to say which one's better, right? You can think of lots of examples of both different strategies being used depending on what type of a species you're looking at. This R and this K are going to be very important. In a minute, you'll know what the R and the K refer to. I've asked that on the final too. What does the K stand for in K-selected species? What does the R stand for? I'm going to show you in a second. Okay, so how about this? A survivorship curve. You all know what that looks like, right? You have a picture in your head of a survivorship curve. Graphically shows the reproductive behavior of a population, shows the relative mortality of individuals in different age classes, must be identical for males and females of the same species, or all of those. guys, most of you got that right. This refers to a reproductive table, right? And obviously I showed you one where the males and females are different for this group. Okay, high levels of juvenile mortality. I didn't really say this, but you probably figured it out. Push the age of first reproduction earlier, later, neither earlier nor later, or either earlier or later. Do you know what that means? It means, let's imagine a lot of the squirrels start dying when they're younger and younger. What do you think selection would do to the age of first reproduction? So in other words, the age at which the little squirrels have their first babies. If you're dying younger and younger, what's selection going to favor? Is it going to favor you having babies earlier? Is it going to favor you having babies later? Or would it be neither earlier or later, or either earlier or later? Can you figure that out? In other words, this one is saying there'd be no selection whatsoever. This one is saying that selection could go either way, and this would say you'd have directional selection in just one direction. Do y'all remember that? Do y'all remember directional selection?
Are you talking about squirrels or humans with the first?
Really anything. You can think squirrels if you want to, but it could be anything. What's going to happen if you start dying young? What's selection going to do about when you first reproduce? Okay, there are two more. And then I'm going to click and click so that I get you closer to the other class. Hopefully that's kind of intuitive, even though I forgot to say it. Okay, ready? Is there one more? Pick an answer. Any answer. There you go. And you all figured it out. Despite you acting confused. Okay, so now we're going to start modeling this. And this is going to be important because you're going to do this tonight a little bit. You're going to do it with some means and you're going to do the computer. The models you're going to be using tonight and tomorrow in lab are more sophisticated than this, but I'm going to start you thinking about how you would do this. It's basically all going to be done with equations, you realize, right? So we want to model changes in this population over time. And as I mentioned before, we're going to actually ignore these two, immigration and emigration, and instead we're going to assume we only gain individuals by birth and we lose individuals by death. So those are the only two we're going to put into our equation. Here we go. What does the little delta mean, that little triangle? Change. And notice we usually use the capital letter N to represent population size. So we're interested in the change in population size over time, and big D we could use to represent the number of births, and big D to represent the number of deaths. And it's really as simple as if I want to know how much the population has changed from one generation to the next, I just basically subtract the number of births from deaths, or deaths from births, right? And that's my change, right? So if I start with 100 individuals, I go to the next generation, and like 20 were born and 10 died, what happened? And now how many are we? 20 were born, 10 died. We started with 100, so now we must be what?
110.
110, right? The change is 10. It's the birth minus the death. And obviously if I had 20, like if I had 10 were born and 20 died, now the change is minus 10, right? So now I'm down to 90, right? That's not particularly hard. Now, of course, we don't really want to deal with these raw numbers. Instead, we'd rather deal with percentages, right? So I want to know what my percent increase or my percent of birth increase is and my percent of deaths is, or my per capita birth rate and death rate. So we represent that with little b and little d, and then you just multiply it by n, which is the population size. So it would be like saying I started with 100 individuals, I had 20% births, and I had 10% deaths, right? It's the same idea, right? And you could get the raw numbers from that. And then we can have this number called R, which is just going to be little b minus little d. And that's basically going to be our growth rate. Yeah? Can you all follow that? Yeah? No? R. Didn't I tell you in a minute I was going to show you an R and a K if I get to it in 2 minutes? There's the R. You're going to understand why it's R in a second. Notice that R could be 0. What does 0 mean? Your population is not growing, right? The birth rate and the death rate are identical. What would it mean if R was positive? That means that your birth rate is greater than your death rate, which means that your population is increasing. And R could be negative. that your death rate is greater than your birth rate, in which case your population is going to be decreasing or declining. Yeah? So now we're going to model population growth, right? And notice we want to be able to look at this thing we call instantaneous rate of growth, right? So the instantaneous per capita rate of increase, which we're going to put kind of like this. And you'll notice that this is basically a derivative, right? That just allows you to estimate what the intrinsic rate of increase is at any instantaneous moment. Okay, there's two different growth models, right? One is exponential, the other one's logistic. So an exponential growth model is limited only by biotic potential, which means how fast can you crank out babies. That's the only thing that limits this model. The number is staggering for most species. Flies, something like, if every flies lay how many eggs? Like a zillion, right? If every egg hatched and lived and grew to a fly, and every one of those laid a zillion eggs, and every one of those survived and hatched, how fast could we increase flies? It becomes staggering, right? Something like 3 or 4 weeks, you could cover the face of the earth 6 feet deep in flies, right? Most organisms have incredibly high biotic potentials. Obviously, most flies don't make it that far, right? Because there are different limiting factors. There's not enough food, there's not enough space, there's not enough resources, there's not enough whatever in order to support all those individuals. So most systems are limited by something like that. So we can think of this biotic potential or this maximum intrinsic rate of increase, but it only can be sustained for a very short period of time in a natural system. But notice that it's a line that basically shoots to the sky. Just to show you a couple examples of this. Here's one where the maximum rate of increase of the biotic potential is 1. What does that mean? It means if we had 100 rabbits, next generation we have 200 rabbits. The next generation we have 400 rabbits. The next generation we have 800 rabbits, right? This would be R equals 0.5. The maximum rate of increase would be 0.5. What does that mean? I have 100 rabbits. The next generation I have 150. The next generation I have 225, right? I'm increasing by 50% each time. Notice the line still goes straight up, right? So just because your R is not 1 doesn't mean the line doesn't go straight up. It's still exponential, right? Elephants. At least in the 60s, we're growing exponentially. How could that be? What do you think happened right about here? They implemented some serious anti-poaching laws, and the little elephants took off, right? Obviously, that can't keep going, right? You could fill the visible universe with elephants in about 10,000 years if they were able to reproduce at biotic potential. Guess who this is? This is us. You got a little blip here about in the 1400s from the plague, but right now we're definitely in exponential growth, right? We're over 7 billion now, and the problem is, where's that line going to level off? It's not going to be pretty when that line levels off, and nobody knows exactly where that line is going to level off. The reason the line levels off is because of this thing called a logistic growth model, which incorporates this letter K. I'm just going to show you this, and then you'll be in exactly the same spot as the other class. Notice that the first part of this model has the biotic potential part, right? K is what we're going to refer to as the carrying capacity. How many individuals can in a particular environment support? So let's imagine you have an environment that can support 1,500 rabbits. What's going to happen when the population size gets really close to 15? What's going to happen? 1,500. What's going to happen when the population size gets really close to 1,500? Like they're at 1,497. What's that going to be? This is going to start to get close to what number? Because you're dividing it by 1,500, it's going to start to get really close to 0, right? It's going to start to get close to 0 over 1,500. If this is 0, what happens here? This becomes 0 and the line levels off. But now let's imagine you can support 1,500 rabbits. There's only 3 rabbits, right? They're like having rabbit party out there, right? 3 rabbits are seriously like, woo! We got resources for 1,500. There's only 3 of us. This number, notice, is what? Very close to 1,500. It's like 1,497 over 1,500, which is almost what? 1, which means basically that line is going straight up. It's basically 1 times whatever the rate of increase is. And so the intrinsic rate of increase, the biotic potential. And so what you'll see is you end up with a line like this. Here is when n is much less than k. The closer n gets to k, the more it starts to level off. And when n reaches k, the line goes flat. So the first part of this is an exponential growth curve, right? But the overall growth curve or growth model is a logistic growth model. You're gonna need this in lab this week. Picture this. Yeah. And we'll pick up right there.